This is an overview of what I want you to be sure to understand in section 2.5. I'm going to take a very light kind of visual look at the first part of this section, the concepts of symmetry and even and odd functions. In the textbook, there are multiple tests for checking algebraically for symmetry and whether a function is even or odd. I'm going to be perfectly happy if you can tell visually whether a function has symmetry and is an even or odd function. Now we already know that parabolas have an axis of symmetry. For any parabola, there's a vertical line through the vertex that if we fold the graph over, it's a mirror image of itself. If a parabola happens to have its vertex on the y-axis, then we say that the axis of symmetry is simply the y-axis. And so what we're looking at specifically today are functions that have symmetry with the y-axis besides the parabola. So this first example here, it's kind of this giant W. It's a rough sketch, sorry about that. But you can see visually that if we were to fold it over the y-axis, it's a mirror image of itself. The same thing here with this function, which is a particular trigonometric function. The formal definition for symmetry at the y-axis is that if we have a value x has a particular y value with it, then the opposite value of x should have the exact same y coordinate going with it. And that would be what the formal test is about. But again, visually, if you can see symmetry at the y-axis, I'm happy. Symmetry with the x-axis would be a shape like this green line here, parabola on its side. The formal definition is that for any given value of x, if it has a y-coordinate, it also has a negative y-coordinate. And we don't see these nearly as often as the symmetry at the y-axis because any graph that's symmetric with the x-axis is not going to be a function. It fails the vertical line test. A circle centered at the origin is a nice example because it has both symmetry with the y-axis and symmetry with the x-axis. Okay, now symmetry with respect to the origin is a little more subtle of a concept. The idea of symmetry with the origin, formally, is that for a given x with a y coordinate, that the opposite value of x produces the opposite y coordinate. And you can tell I didn't draw this very well and didn't quite hit the point. This is a graph of the cube root of x, and it does have symmetry with respect to the origin. Visually, what I look for when I'm looking for symmetry with respect to the origin, if I was to take what's happening here in the first quadrant, fold it over the x-axis, and then fold it over the y-axis, do I have a mirror image then? So if we look at this black line, flip it over the x-axis, it'd look like this. Flip it over the y-axis, then I've got my mirror image. The blue line here is a graph of 1 over x. If it has a vertical asymptote, so it's in two pieces, something we'll come back to later. But again, if you were to graph 1 over x on your calculator, take this part of the graph, flip it over the x-axis, and then would give us something like this. Flip it over the y-axis, we see we get that mirror image. Here's another one over here at the red line, has symmetry with respect to the origin. Okay, a little terminology. An even function is a function that has symmetry at the y-axis, and an odd function has symmetry with the origin. Again, we're not talking about symmetry with the x-axis, because if you have symmetry with the x-axis, it's not a function. But I do want to jump so two different words for essentially the same thing, but jumping ahead a second, for something that's going to happen in the next chapter, polynomials. You may remember from previous algebra classes, a polynomial are those nice functions where we have a constant times x to a power, plus a constant times x to a power, plus a constant times x to a power. If you create a polynomial and all the exponents on the x, like this one here, 6, 2, and 0, if all the exponents are even, that's going to be an even function, and it will have symmetry at the y-axis. And if you have a polynomial where all the exponents are odd, x to the 3, x to the 1, go ahead and graph that on your calculator. You're going to see it has symmetry with the origin. So that's just where those terms come from, that the even function has symmetry at the y-axis and the odd function has symmetry at the origin. Okay, translations of graphs. You're definitely going to want to play with your calculator a little bit as you get the hang of this. And we saw a little bit of this again with parabolas, and so some of those concepts with the graphing and moving parabolas around applies to any function. So this first example here, I'm looking at f of x equals x squared, our simplest parabola. That's roughly the black line right here. And then I'm looking at a couple variations, x squared plus 5, x squared subtract 2. I'm sorry, that's in the way. There we go, x squared subtract 2. So x squared subtract 2 is the blue line, x squared plus 5 is the red line here. And what's happening is if we take any function, tack a plus 5 on the end, it's going to shift that function, the graph of that function vertically up 5 units. If we subtract 2 off the end of any function, it's the exact same graph, but shifted down 2. Again, play around with this on your calculator, and you'll get the hang of it very quickly. This one's slightly trickier. This is going to be a horizontal shift. And I'm using the absolute value function here. If you haven't graphed the absolute value function on your calculator before, you can find it by pressing the math key, arrow to the right, and then option 1 gives you ABS, which is absolute value. So if you do have your calculator, graph the absolute value of x, the absolute value of x plus 4, and the absolute value of x subtract 1. So here the constants being added or subtracted to the independent variable, the x, inside the function. And what happens, so the basic absolute value of x is a V-shaped graph with its vertex at the origin. The absolute value of x plus 4 is the same graph, but it's shifted left 4, whereas the absolute value of x subtract 1 is this one right here, and it's shifted right 1. So these horizontal, the left and right shifts, are the opposite direction of what you might think at first when you look at the function. So x plus 4 is going to shift it left, x subtract 1 is going to shift it right. Okay. Vertical stretching and compressing. Using x cubed here as my basic function. 4 times the function, 1/2 times the function. When we graph it, we're going to see that 4 times x cubed is taller and skinnier than the graph of x cubed, so it's 4 times as tall. And 1/2 times the function is half as tall. And just kind of a side note here, again, for something that's coming up in polynomials in the next chapter. When you multiply a function by a constant, the x-intercepts will not change, because the x-intercept is the value of x, where y is 0, and if we take 0 times any number, it's still 0. So any x-intercept will stay put as we make these functions taller or shorter. We're going to skip over horizontal compressing and shifting. Okay. Square root of x plus 2. I went with a little bit more complicated looking basic function here to flip around just to make it a little easier to see what's happening. And what I want to look at is what happens if I take the function, multiply it by a negative, and compare that to if I go inside the function and replace the x with a negative x. So we're changing the y values to the opposite values of x, and we're changing the x values to opposite values of x. So the red line here is my basic square root of x plus 2. The blue line is what I get if I take that square root of x plus 2 and put a negative in front of it, multiply the entire function by -1. It will reflect over the x-axis. Whereas if I go inside the function and replace the x with the negative x, I get the green line here, a reflection over the y-axis. And kind of going the different way. It's a little messy here. So whatever, any old function h of x, if I take h of x and I replace the x with an x subtract 3 and I tack a plus 2 on the end of it, that function is going to shift right 3 and up 2. So I just kind of drew an arbitrary odd looking function here, this black one here. If the graph of h of x subtract 3 plus 2 will be over 3, right 3, and up 2. If I take the function, again, any arbitrary function, multiply it by a negative, that'll flip it over the x-axis, and then add 2, it'll go up 2. Order of operations applies here. Multiplication always comes before addition. So the reflection is going to happen first, and then the shift of up 2. So if I take my black function here, reflect it over the x-axis, I've got this rather messy dotted blue line here, and then it would shift up 2. And so this blue graph here would be my final function of negative h of x plus 2. And if I take 2 times h of negative x, the negative x is inside the parentheses, so that reflection is going to happen first. Replacing x with negative x will give me a reflection over the y-axis, so that would be a flip here from my black line over to this dotted green line. That would be h of negative x, and then 2 times it is going to stretch it and make each y value twice as big. So a value of 4 would become 8, a value of 5 would become 10. If I had a value of 0, this one didn't have a x-intercept, and I doubled it, it would still be there at the 0.